All right, welcome everybody to the next installment of New York Combinatorics seminar. Today we've got Athar Abdul-Quader, who's going to tell us about lattices of elementary substructures. Take it away.
Uh,
Wait. Scroll over the click once.
Which one do I scroll to? Left side?
Yeah,
Left side?
it's up there now. So
Oh,
click
okay.
once and then
Perfect. All right. So this is I'll send Deepak. This is the first time I'm giving this talk to to an audience of non-logicians. Forgive me, but I'm gonna start with a little bit of a background in logic, so that we can talk about elementary substructures briefly, and then I can get into this problem, which has a lot of interesting combinatorial content, and that's why I'm bringing it to you guys, because I think that I'd like to sort of put it in the back of your brain if anyone wants to think about this and has ideas. I would love to talk about it with anyone, particularly people who are more expert on the combinatorial side. So first of all, so what's a structure? A structure, you all know, it's a set with some operations, relations, and things like that. For the purposes of this talk, you want to think of the natural numbers with addition, multiplication, and the ordering, right? And so that forms a structure that we're pretty familiar with as like as a semiring, an ordered semiring, and specifically discretely ordered semiring. And I'm gonna introduce or I'm gonna use this sort of logical formalism to kind of describe that. So like you can say that every natural number has an immediate successor, and this is expressed formally with this logical statement. This turnstile here is I guess it's models, but I'll usually say and the natural numbers think this, or the natural numbers believe this, or this is true in the natural numbers. Or I think really the right word would be satisfies, but yeah, I'll be a little bit informal. And then, of course, the normal sort of properties of addition and multiplication. So the natural numbers have all the things that you think of as in terms of rings. It's the semi-ring structure, right? So the non-negative part. I'll start natural numbers with 0. So we have like the non-negative part of a discretely ordered semi-ring. And you can essentially express all of these in this sort of language, language of first order logic with these particular symbols, right? 0, 1, plus, times, and less than. Okay. And the basics of like what you do in the first day of logic, you build up formulas. So you can say things like x is less than y, or x times y is less than z, and things like that. And you can, using 0 and 1, you can get essentially an addition and multiplication, you get sort of polynomials on x and y, and talk about polynomial equations and things like that. And then those are sort of the basic things, and then you add in conjunctions, disjunctions, negations, and then quantifiers. Yeah. Um, and so this is a formula, x is greater than 1, and whenever a and b are, for any a and b, if a times b is equal to x, then one of them is x. That is a formula that expresses x as a prime number. And so most number theoretic things that you would imagine can be expressed sort of in this language. And of course, you get 5, 2 is true, and 5, 6 is false, right? And so just to give you the notation here. Okay, so let's sort of suppose we have any discretely ordered semiring, and you can imagine what the kind of algebraic axioms would be. So I'm not going to list them all, but kind of open up a textbook on ring theory and write it all out. Plus what you think the natural axioms for ordering are. So suppose you have 2 of them. If one of them is a subset of the other, right, and they agree on the operations and the relations, right, the inequalities, then we call the smaller one a substructure, and the larger one an extension. Okay, it's more or less immediate that the natural numbers are a substructure of any discretely ordered semiring, because I am insisting on a 0 and a 1, and then I'm insisting on addition, and so you get every natural number, and you will get essentially that it has to be the initial part, right? The initial segment of any one of those. And so it will any discretely ordered semiring will agree with the natural numbers about addition and multiplication and less than, right, for natural numbers. It's not too hard to see that if you have a M is a substructure of N, then they're going to agree, and this is more general. This is about sort of general logical structures. They'll agree about the truth of any statement, any statement involving any first order statement involving parameters from the smaller model, right? So involving elements of this, the truth about anything that you could say about M, right? As long as you don't ask about quantifiers, right? So if you're just really talking about the algebraic kind of statements, the things about polynomials and less than, things like that. Those, if they agree about addition and multiplication, then they're going to agree about conjunctions of sentences about addition and multiplication and things like that. And, an elementary extension is when you insist that the two sets agree about not just the quantifier-free statements, but all statements, so including formulas that involve quantifiers. Okay, so something could be true for every single x down here, and then you say for all x, p of x is true. Then you're going to have to insist that that's true in the larger structure, which might not necessarily hold in general. But if you do get that, you get what we call an elementary extension, and we write it with this curly sort of less sensitive. Right. I've used these words like statements and formulas. So a formula we talk about is built up a certain way using inductively using addition, multiplication. I'll say a statement is a formula without free variables. Yeah.
Yeah, just a quick question on the having to satisfy the same formulas.
Mhm.
You use the example like we could use a for all quantifier. Now we're quantifying over everything in the
Yeah,
structure, not just the things.
So if so, let's say you start with the natural numbers, right? If you quantify over everything in the natural numbers and something is true there, right? So it's true about every natural number. Then if you want to insist on building an elementary extension, then that elementary extension should also make sure that that statement is true about even all those bigger elements. Yeah, yeah. Exactly. Good question. Okay, so we have formulas, we build up these formulas inductively, we talk about statements, they're formulas without free variables. Those are the ones that you can actually assert truth or falsity of, right? Like you can actually say, okay, phi is true, rather than saying phi is true about 6 or 2 or something. You take a set of formulas, or a set of statements, if it's consistent, right? So they're not contradictory. So you don't have like you don't throw in a formula, a statement phi and its negation, or if you kind of put some kind of proof theory on it, like you kind of build some basic sort of structure of what you think a proof should be, like modus ponens and stuff like that. You don't get any kind of contradiction on the with the deductive closures. Then you call that set a theory. And a model is a set or a structure satisfying all the statements in a particular theory. Okay. And this is a sort of a really important result in model theory and in first order logic. Essentially, the idea is that if you have a theory that's consistent, to say that it's consistent is to say that it doesn't prove some kind of contradiction, right? And to say that it doesn't prove a contradiction is to say that no finite, like if it did prove a contradiction, then you have a proof that's a finite set of, sort of deductions. And so there's only a finite set of statements from this T, which I shouldn't be pointing because there's only a finite set of statements from this T that would be used in getting some kind of contradiction. And so to say that a theory is consistent is say that it's finitely consistent, say that every finite subset of it is consistent. And something that is not obvious, but it really, if you want to do anything involving model theory, you really want to insist on this, which is if you have a consistent theory, then it has, then it has a model, right? Or if you have a finite set of statements that does not imply any kind of contradiction, then there should be some model which all of those are true. And so if you take those two ingredients, you get this result called the compactness theorem, which says a theory has a model if and only if every finite subset of it has a model. Again, it's sort of it's a pretty nice result that you kind of want to insist on if you're going to do model theory, and you essentially insist on it for that reason of like making sure like what is a consistency even mean otherwise, right? And so what's unfortunate or what's fortunate for me, what I think is really nice about it is that once you have this, then you get all kinds of weird sort of non-standard models. And so when we talk about how we get those, so once you have the compactness theorem, you can start writing down a bunch of sentences, each of which any finite set of that is consistent, but then realizing all of them at once would insist on something that goes out of your base structure. So to back up for a second, right, the idea behind like maybe this is ahistorical, but an idea behind sort of axiomatizing arithmetic or axiomatizing set theory or axiomatizing mathematics like originally one would hope that you can kind of come up with the set of axioms of mathematics, right? And of course that project failed, but it was a hope that you could insist on, okay, these are the things that you need just to prove everything number theoretic, right? And and so Dedekind and Peano actually did that. They wrote down these axioms, and they thought of it in what I refer to as a second order way, which I won't really define. But if you write down those axioms in first order logic, you will very quickly get that there are models of those axioms that are not just the natural numbers, right? And so they will be discretely ordered rings, but they'll have infinite elements or non-standard elements. And that's sort of the basis of non-standard models of arithmetic, and that's where all that comes from. I'll say a little bit about that in these next couple of slides, but so we have theories, we have formulas, these are types, which is sort of a set of formulas with a consistent set of formulas. So any finite subset of that, there is some any finite subset of that can be made consistent, can be realized in some way. And so if you have a type and a model, you say that an element realize that model if that element is has if every formula is true about that element in that model. Okay, and so if you have a model and a consistent type that's not realized, then the compactness theorem says it has to be realized somewhere, right? So it will be essentially you can prove that there will be an elementary extension realizing that particular type. And so what I want to do is then use this and the compactness theorem to actually get models of Peano arithmetic that are not the natural numbers. So back on a model of arithmetic is a discretely ordered semiring, so a set, addition, multiplication, less than a 0 and 1 that has this sort of discretely ordered semiring structure with this with the additional requirement that the induction principle holds. And so you get induction for every first order formula. So if you have a formula, you know, and so it just and naturally what you would think of as like the principle of induction for each individual property, I guess, first order property. And so the natural numbers form, you know, the classic standard model of arithmetic. If you take those axioms and you can write down, these are, again, I keep doing this. The number one is actually a finite set of axioms. The axioms are discretely ordered semirings. You can write them down. Number two is an infinite set of formulas, but there's like kind of a scheme, right? Like you can it's an axiom scheme, I guess is what I would say. But it's kind of like a it's like recursive. It's computably enumerable is the way I'd say it. If you write down all of these, right, and you throw in a bunch of formulas that say C is some element, right? C is some constant that's not talked about, and C is greater than 0, and C is greater than 1, and C is greater than 1 plus 1, and C is greater than 1 plus 1 plus 1. You write down each one of these, then the compactness theorem will apply, and you'll get a finitely consistent set of formulas. But if you were to realize it, that C would have to be greater than every natural number n, and that will give you a non-standard model. Right? Okay. I wanted to give a couple of really basic results about arithmetic. Well, I think I do need the word here. If you have a formula, arithmetic has this, a Peano Arithmetic has this nice property that if a formula is realized, if there's an x that makes the formula true, if there's an x that makes this formula true, then there's actually a smallest x, right? And this is, of course, it's the well ordering of the natural numbers, right? But well ordering is actually induction, right? That's provable from the axioms of arithmetic, from this induction axiom that if you have this, assuming that this phi is some formula in first order logic, then there is some definable way of getting this f. There's some way that you can express this as a formula in first order logic. And in particular, that's this, right? It says if you have a formula phi of xy, you can say, well, define this formula c of xy, which will say this must be true, but this x must be the smallest one that makes that true. And it's the axioms of arithmetic will prove that if there, whenever there is a v with such an x making phi of xy, phi of x be true, then there is a x making c of x be true. Right? Something like that. So, oh, sorry, and I didn't say the word that I wanted to say on the slide, which is we call a function that's defined like that a Skolem function. Okay. There's a more general definition of Skolem function, which is what I have at the top here. But in your mind, for the purposes of this talk, think of it as the smallest witness to some property, or the smallest the smallest element of a particular definable set. And this is if the set is definable, the least element of that set is definable in arithmetic. And so set theorists always have this issue of like, is this property like can this function sort of exist without this axiom of choice or whatever? And we don't have this worry in arithmetic because right we always have choice functions, which is just the smallest thing making something true. Okay. And so this kind of choice function we call a Skolem function. And if you look at the collection of all Skolem functions, and you take any set and you look at like the closure of that set under those Skolem functions, you will get an elementary submodel of the model that you started with. And it doesn't take too much work to see that, but and that's actually the smallest elementary submodel, right? So if you have a set A in a model M, then the Skolem closure of A is going to be the smallest elementary submodel of M containing A. And if I have a M and an elementary extension N, and I take take an element or a set in this larger model N, then I can look at the skull enclosure of everything in the base model plus this new element, and I'll call that M of A, right? And so in the top case, if I start with model M and I look at elements in, yeah, keep doing this if you forget. If I start with a model M and I look at subset here and I look at its skull enclosure, I get an elementary submodel. In this case, if I start with a model, an elementary extension and an element in the larger model, then I look at this M of A, that's going to be an intermediate model. It's going to be an elementary extension of the base model and an elementary submodel of the larger one. Okay. So all of that is the preliminaries, and I apologize, that took longer than I had hoped. But any questions or anything about the preliminaries before I start talking about things that I think are more lattice theoretic? Although there'll be a lot of this. Okay. Yeah.
It's just a symbol, the bar was emoji that it's.
This bar?
Yeah.
This bar means the satisfies, right? So I'll say a model of arithmetic or a model that satisfies Peano Arithmetic. Yeah.
That's my first time.
Yeah, that's that turnstile. Yeah. Okay. Anything else?
And this is great.
Sorry?
Quality is like
This-
enough or small exposure.
This one?
Yeah.
This is called elementary substructure, right? And so that's the set that's the sense that this is a subset of this. They agree on the truth of all formulas, all formulas involving elements in this smaller set.
Yeah, like when we do the subgroups, like we do this.
Yeah, so like a subgroup will be a substructure, but not always an elementary substructure, right? So, yeah. Okay. So if I take a model of arithmetic and I look at all of its elementary substructures, this actually forms a lattice. I guess I didn't write that it forms a lattice. I just said it's called the substructure. So it forms a lattice. This is not entirely obvious, but it is an exercise that you could give a graduate student in logic, I guess. I don't know if you gave this as an exercise at one point, but I think this is an exercise that you could. Okay. So the meat is the intersection, right? And so the intersection of two elementary substructures is an elementary substructure. That's an exercise that needs to be checked. The join is the skull enclosure of the union, and so the union is not immediate, but you do need this thing that I talked about, these skull enclosures. Similarly, if you have if you have an elementary extension, then the set of everything in between, right? The set of what we call interstructures forms a lattice as well, and this is called the interstructure lattice. So the simplest example, of course, is the natural numbers. This has no elementary substructures, right? Because I said this, that if it's sort of immediate that any discretely ordered semiring has to contain the natural numbers. And so this is the simplest possible lattice, is the one element lattice. Okay, so what do we know about these particular lattices? And embarrassingly, the answer is very little. And the problem is about 60-ish, 70-ish years old. And so, but I'm gonna summarize everything we know in essentially 2 slides. Everything that all the restrictions that we know. So, some basic definitions. So if you an element of a lattice is compact if whenever it's below a join, then it's below a finite subjoin. Okay. A lattice is algebraic if it's complete and compactly generated. So each element is the supremum of of a set of compact elements. Okay, and a lattice is kappa algebraic for some cardinality kappa if it's algebraic and each element has each compact element has less than kappa many compact predecessors. Okay, so in a in the next slide, I'm gonna talk about Aleph-1 algebraic. So Aleph-1 algebraic would mean you have each compact element has countably many compact predecessors. Okay. So what are the compact elements in a substructure lattice or an interstructure lattice? In a substructure lattice, the compact elements are exactly the skull enclosures of single elements. They're exactly the finitely generated submodels. Okay. And similarly, the compact elements of interstructure lattices are exactly the models that are finitely generated over the base model. And in arithmetic, finitely generated, there's a lot of coding. So you can code finite sequences by a single element. And so finitely generating means essentially generated by a single element. And so skull enclosures of single elements and M of A for single elements A. And so what do you get? So the compact elements here in these lattices are going to be these like M of A or skull enclosure of A, these finitely generated elements. And if you have a model of arithmetic and you have some A in M, the skull enclosure of A is, well, how many formulas actually are, so skull enclosures are formed by like these functions that are sort of picking out the least element of different formulas. And so how many formulas are there? Well, it's sort of, if you go through what is a formula and all that, then there's only countably many. And so if there's only countably many formulas, there's only countably many skull functions. So each element, each skull enclosure would be countable, and it would have countably many predecessors, right? And so you'll get that. If you look at the interstructure lattice, if your base model has cardinality kappa, the M of A's will have size kappa, and so similarly there'll be kappa many, at most kappa many predecessors of those M of A's. And all of this is to say, this is actually all that we can say, or these are the only things we can like rule out. Any lattice that's not algebraic, any lattice that's not Aleph-1 algebraic can't be a substructure lattice and similar. And so if you look at these definitions for a second, the natural sort of or a very quick question that emerges is, can we say anything about finite lattices? Right. Every finite lattice, every element in a finite lattice is compact, and every element in a finite lattice has finitely many predecessors. So there's really nothing to say. Finite lattices are always complete. They're always algebraic. They're always Aleph-1 algebraic. There's really nothing you can say that restricts anything about any finite lattice. And so that's like that. I don't know if I wrote it out as like that is the question. This is an open question in models of arithmetic, which I should have written down at this point, but I cut down a lot of my slides, and so I probably erased it at some point. Which is, given a finite lattice L, can it be realized as the lattice of elementary substructures of a model of arithmetic, right? And so for the rest of today, I'm going to go through a little bit of history and a little bit of hopefully a flavor of some of the techniques, so you can see what the combinatorial flavor of these things is. Just to get a sense of like why this is an interesting problem. Okay, so and one of the things that's interesting to me, like from a model theoretic sense and less a combinatoric sense, is that all the results kind of have this flavor of like every model of arithmetic has an extension realizing a particular lattice, or every countable model of arithmetic, or every sort of some like large classes of models have this particular thing. It's never for this particular lattice, I have to build this particular model of arithmetic to do something. It's always like it can always be realized or it can never be realized, so something like that. And so the one of the first results on this was due to Gaifman. Both of these are in the same paper. Every model of arithmetic has a minimal elementary end extension. And so what is that? That is an elementary extension realizing the lattice 2, right? The 2-element chain. And he builds on this, and he develops a really a nice technique that he can use to essentially build for any Boolean algebra. He can build an elementary extension realizing that particular Boolean algebra. And then it was an open question of whether that can be done for any finite distributive lattice, and that was answered, but then an even better answer was given for any distributive lattice as long as it's alpha algebraic, right? And so distributed lattice has the distributivity clause, so joins and meets distribute over each other, right? Any alpha algebraic distributive lattice can be realized as an elementary as a substructure lattice or an interstructure lattice. This is the simplest example of a non-distributed lattice, or one of the simplest examples of a non-distributed lattice. So this is a modular lattice on 3 atoms. And so Jeff Paris and Jim Schmerl in the 70s and 80s proved that there are models of arithmetic that can realize this as a substructure lattice. And I'm not going to say too much about this one, but in particular, there's no elementary extension of the natural numbers that can do this. So there are models of this, but they're not elementary. They're not elementary extensions of the standard model. And yeah, it's sort of not much I could say about that right now. This is another example of a non-distributed lattice. This is the pentagon lattice, N5. Oh, so by the way, this one is called M3, the modular lattice on 3 atoms, and this one is called N5, which is a non-modular lattice. And it's the simplest non-modular lattice. It was proved in the 70s by Alex Wilkie that there are models of arithmetic that can realize this, and he actually did it as an extension of the natural number, so it's different from the previous result. Jim Schmerl proved that actually we don't know if you can do the exact. We certainly can't use that exact same result in the uncountable case. So you can do this for every countable model of arithmetic. You can build an elementary extension realizing the pentagon, this lattice is referred to as a pentagon lattice, but you can't necessarily use that same technique for uncountable models. So it's the things that are open around it, I'll skip for now. So what's the simplest lattice for which we don't have a positive answer for? So this is lattice, the simplest lattice that we don't have an answer for, or that's open, is M16. So M3 was a bottom and top and 3 atoms. M16 is a bottom and top and 16 atoms. And so in general, Mn, we start with n at least 3, is these modular lattices on n elements. And these are all, for n at least 3, these are all non-distributive. Like I said, the distributive lattices we know the answer to. For M16, this is the smallest case for which is unknown. It's sort of, if I have enough time to say why, there's something strange that about, like, essentially every number below 16 sort of has some property making it sort of work, and I don't know exactly, like, it's a strange thing. And so this is the question. I said I should have written it earlier. For which lattices L can these lattices be realized? And or if I start with the model M, when can I build an extension realizing it as the interstructure lattices? And so usually the answers are every model of arithmetic has something, or every countable model. Maybe we only know things about the countable models, maybe only know things about the non-standard ones, etc. So let me say a bit about the techniques that are used in this, and this is where some of the combinatorics of these lattices come into play. So given a set, you can look at the lattice of equivalence relations on that set, right? And so the bottom element is the discrete relation, and the top element is the trivial relation. Everything is equivalent to it. And so if you take a lattice, then you have a representation on that lattice is an injection into the lattice of equivalence relations that sends the bottom element of L to the trivial relation, the top element to the discrete relation, and then switches joins to meets. Okay. So so a very simple example is the lattice 2, right? So lattice 2 just has a bottom and a top. So you're gonna represent the lattice 2 by saying alpha of 0 is trivial, alpha of 1 is discrete. Okay. Let's say I start with a model of PA, a countable model of arithmetic, and I want to build an elementary extension realizing this lattice 2. How would I do this? So I show somehow that every definable equivalence relation, every equivalence relation here, I can find some infinite, as unbounded, every large definable set B, where this theta is either trivial or discrete. And that's essentially just pigeonhole. Right? Like you look at how many equivalence classes are in theta. Okay, does theta if theta has finitely many equivalence classes, one of them has to be infinite. Right? Okay. And you bound, in PA the analog of finite versus infinite is bounded versus unbounded. Right? But the same logic kind of holds. You can pigeonhole. And so you pigeonhole if it has if none of them are, if none of the classes are infinite, you just take the smallest element of each class and then you get an infinite discrete set. Okay. And so then there's essentially a standard technique which I'm going to skip over because I'm running low on time, but the standard technique will essentially be able, and if you remember earlier I said we build elementary extensions by coming up with these types, and we show these types are consistent, and then if it's realized, then we get an elementary extension. Okay, or if it's consistent, it's realized in some elementary extension, right? And so you can kind of do that, and essentially what you can do is build the type, making sure that every single one of these thetas, every single equivalence relation, definable equivalence relation, will be made trivial or discrete. And if you think about what that means, it means every single function, every definable function on the model will be made one-to-one or constant. And if you do that, then you'll get that every element in that new model is either invertible, like something that can be sent back to the generator, or it was in the base model. And so those are the two options. I'm gonna skip over the details here because I know I'm way too slow here. But anyway, what I want you to take out of that is, if I want to build the extension, a minimal extension, I essentially need the pigeonhole principle. Okay, very simple combinatorial. So what do I do if I want to build this lattice? So this is a Boolean algebra on 2 elements. And so here I'm going to define a representation on the set of pairs. And my representation, this is ugly. So I'm going to talk about here. 0 has to be sent to the trivial relation. 1 has to be discrete. Okay, so I'm going to define a representation on the set of pairs, and so think of the set of unordered pairs, but you pick out the smaller element, right, and the bigger element. So you say that 2 pairs are equivalent according to A if their smaller elements are exactly equal, and this one will be if their larger elements are exactly equal, right? And so that gives you and if you think about what happens if you look at their intersection or their union, right, of those two, right, what happens to meets and joins in that, you will get trivial or discrete, right? Because if you're on the set of pairs and first and the second element are equivalent, then yeah. Okay, so am I making sense? Okay. So we have a representation on the set of pairs, trivial discrete, equality on the first coordinate, equality on the second coordinate. What we need a combinatorial lemma instead of the pigeonhole principle. What's the combinatorial lemma that we need here? Well, this is essentially a canonical form of Ramsey's theorem, right? So Ramsey's theorem for pairs says that if you color the pairs with finitely many colors, you can find an infinite set where all the pairs in that infinite set are monochromatic, right? But what if you don't have finitely many colors? What if you go off to infinity? So if you color the pairs with possibly an unbounded number of colors, then you can get an infinite set where all the pairs in that are one of these four options I said. Either it's monochromatic, or it's each pair is differently colored, or the color is dependent on the first coordinate, or the color is dependent on the second coordinate. And that's canonical Ramsey's theorem due to Erdos and Rado in 1950. Let's put it up for a second for me to think about what it says. Right, and so you have a coloring of the pairs, you can get an infinite set. And what's nice is that you get an infinite set, and then you kind of thin down what you're looking at. Instead of looking at the pairs of natural numbers, you're now going to look at the pairs of x's. But what's, sort of, these are going to look very similar to these, right? And so then you can kind of do this inductively and continue on. So if I did this for one function f, I could do this for, if I enumerate all the f's, I can kind of get a similar a descending sequence of definable sets in this way. And so I'm not gonna go again. This is kind of the analog to what I skipped over earlier, but essentially, if you just do what I skipped over for the minimal extension too, you can kind of show that you'll end up getting this.
I know there's much more to say about it, but maybe this is worth saying that for instance, with Erdős, Rado, and maybe further advanced theorems, to have some connection to arbitrary models of PA.
Mhm.
This is, right, so that there is some element of probability.
Right, okay, so this is actually good to say. So pigeonhole is of course provable in just PA, right?
Or enough.
In right, but yeah. Well, has to be provable in something. I guess and logic, right? Canonical Ramsey's theorem. So first of all, you can't quite state this in the language of arithmetic because you are quantifying over sets of numbers now. And so how do you say this? So we can go to what's called second order arithmetic, where we have a set of numbers and then a set of subsets, and there's all these areas that study like how strong do you need second order axioms to be able to prove things. And so there are these what are called these big five axioms. So essentially, when you have a model of arithmetic, you can immediately look at all the sets that are definable, and you get a model of what's called arithmetical comprehension, which is a second order scheme, or a second order. It's not a scheme, it's actually finitely axial, but a second order sort of system that has the set of numbers and the set of definable sets. And this is provable from that, right? And in what's arithmetical comprehension means that if you define something using like the set theoretic comprehension axiom, like if the set of all x such that some property holds, as long as that property is arithmetically expressible, so expressible in the first order language, then that set can be realized. And so this result is not just provable in HCM, it's apparently equivalent to this. And so there are people who study like these different combinatorial results, these different combinatorial properties. What are the sort of second order arithmetical strength or second order logical strength of these axioms? It's a really interesting area of mathematics of logic and called reverse math. And a lot of the combinatorial principles are actually really hard to pin down. So apparently Ramsey's theorem for pairs is somewhere in between this and there's like a whole kind of strange it's like there are these five axiom schemes that most areas of math fit into, and then a lot of the combinatorics is like kind of off to the side. So it's a very strange thing that unfortunately I don't know enough about, but I think there's something interesting going on in some of the ones that we're using. So in the couple minutes that I have remaining, let me say a little bit more about like how's this problem attacked more generally, and also why is this problem, you know, sort of kind of interesting, and why I think this problem should be interesting to combinatorialists. What do you call yourselves? There are, and I skipped certain definitions. There's a really interesting connection between this problem, lattices of elementary substructures, and the finite congruence lattice representation problem. Finite lattice representation problem, I think it's called. All right, so the finite lattice representation problem asks, can every lattice be the congruence lattice of some finite algebra? Okay, so let me give the definitions so I can state that properly. All right, an algebra is a set with some operations on it. A congruence is an equivalence relation that commutes with all the operations in a particular algebra. And so the set of all congruences forms a sublattice of the set of all equivalence relations. And so this is called a congruence lattice. If I take this the set to be finite, then this is a finite congruence lattice. A congruence representation is a representation, so alpha from L to some EQ of A, but it's a representation that's actually an isomorphism between L and a congruence algebra. Okay. If it's well, the dual of a congruence algebra, because I reversed the ordering, right? If a representation, if the algebra can be taken to finite, right? If it's a finite congruence algebra, then we call this a finite congruence representation. What's known is that every algebraic lattice has a congruence representation. So that includes the finite lattices. But what's unknown is, does every finite lattice have a finite congruence representation? That seems very strange to me, but it's a really interesting thing, because saying that every algebraic lattice has a congruence representation is saying essentially there's very little restriction on what a congruence algebra can look like. A congruence algebra can look like any possible algebraic lattice. The only restriction is it has to be an algebraic lattice. Okay. Now, if I want to know which finite lattices can be these congruence algebras, all finite lattices are algebraic, so we don't know if there's any other restriction on that, and that's unknown if like there are, you know, any actual restrictions. And so Jim Schmerl in the 90s proved that that essentially you can reduce the problem of the lattice problem for models of arithmetic to the finite lattice representation problem. And to actually do this, he used the Pommel-Voigt theorem, which, if you don't know about it, it's a canonical form of the Hales-Jewett theorem, which I didn't know about either. So I'm gonna say a little bit about it. I'm gonna skip over this, but this is essentially me trying to motivate this particular result. But the Hales-Jewett theorem says every finite set A and every M, there's an N such that any finite coloring on A to the N has a monochromatic M-dimensional subset. Okay, the canonical version of this says, so this is akin to the canonical version of Ramsey's theorem for pairs that I mentioned earlier, right? So now you're going to get rid of the word finite here. And so you're going to say any coloring on A to N. So any set A and every M, you can find some N such that any coloring on A to N. And so a coloring is an equivalence relation on A to N. You can find an M-dimensional subset where it's not necessarily monochromatic, but it's canonical in whatever way. So canonical meaning it's really just some equivalence relation on the original finite set, just to the mth power. Okay, in some sense, and this is actually what this this lattice I said was realized in the 80s. This was actually how they did this is how Jim Schmerl did this is by building sort of larger and larger representations of this using this result, this primal void theorem. And then in the 90s, he realized that you could do that for any congruence algebra, or for any lattice which had a finite congruence representation. And again, I'll skip the actual proofs because they're too technical. So what's known? Again, I mentioned what's known in every algebraic lattice is isomorphic to a congruence algebra. The finite lattice representation problem is apparently like a really, a long-standing open problem in universal algebra, and it would be quite interesting if there's any sort of any movement on there. I don't know anything about that. Because so certainly it'll be interesting on its own right, because being able to say are there any restrictions on what congruent algebras can be is a strange thing. But in terms of the problem about lattices of elementary substructures, we really don't have any other techniques. So everything that we know we can realize, even if we found other ways to do it, those particular lattices that can be realized, all of them have finite congruence representation, right? And so everything that I've said, every finite lattice that I've mentioned, so every finite distributive lattice, for example, the pentagon lattice, the lattice M3, the lattices M3 through M15 for various reasons that I don't totally understand. There's somehow has something to do with like prime, powers of primes plus 1, and then
Say that we don't stop at M16. There are infinite.
There are infinitely many.
names for which-
there are infinitely many. There's right, and so there's a very large class of lattices that we know are these, and so we just have no reason to believe that M16 wouldn't be, right? It's just it hasn't been realized as a congruence algebra, and so it's unknown whether there is a truly different construction of a model of arithmetic with a particular substructure lattice. And truly different in the sense of like, is there a lattice for which we don't know the answer for the congruence lattice problem, but we are able to answer for this one? And that so far the answer is no, but that would be sort of strange. So I'll stop there. So my former advisor and I have written a survey of this more for logicians that I spent a lot of time trying to really explain the techniques and motivate the techniques using particular examples. And there's a couple of papers. These are all not very readable to combinatorials, but I'm happy to talk about the problem with anyone who's interested in it, because I think there's a lot. I think that the methods in logic are not totally exhausted, but they've been pushed quite hard, and I think other people need to look at this problem as well. And so I think it'll be really nice to have some fresh eyes on it. All right, I'll stop. Thank you.
First, any questions on Zoom? How about in person? Any questions in person? So like,
Mhm.
when you, what kinds of combinatorial, like different, what would you,
Mhm.
what do you think would help combinatorially, like different theorems, like canonical versions of
Yeah.
Ramsey type things? Or
Yes. And so maybe this is would be bad if I write on the board there.
Just move
But
this.
I mean, I don't really know what I'd write on the board. I don't really know what the theorem would be, but like the combinatorics about the pentagon, for example, are very different. And so there's something interesting about like, okay, so what's the representation on the pentagon? You still do like the set of pairs. Okay. And what does the representation here look like? And I might get this wrong, but you can do, so equality on the first coordinate, equality on the second coordinate, right? And then this is trivial, this is discrete, right? And so what is this one? That's sort of, it looks like one of the ones I said before, it looks like B2, right? But what is this one? This is, so X1, Y1, is going to be equivalent to X2, Y2, according to this one, so I'll just be, right? If X1 is equal to X2 and Y1 is congruent to Y2 mod 2 to the X, with, you know, right, mod that. And I don't have an answer to your actual question, but there's something interesting. So there are other representations that you can use, but this one somehow seems to work. And there's something interesting about this that would be like, so is there some kind of analogous canonicity kind of result that one could get? And if you dig really deep into the proof that so I mentioned it was proved in the 70s, you get some kind of canonicity, but it's weird. And so is there a simpler way to do something like that? Right. And I don't know what the right, I don't even know what the right question is. You know what I mean? Like I feel like there's something combinatorial here, and I want someone who has a better eye for combinatorics to look at it and be like, what is clear? And for a long time that was Jim Schmerl, who was a logician, but really has a great eye for combinatorics. And has been working on this problem for the last like 50 years. So but really has been the only person who's worked on this problem for the last 40 years. So if you saw the names and dates of it, a lot of that from the 60s and 70s. And then the last date I put up, I think, was 93. There's a lot more results since 93, but it's all due to one name, Jim Schmerl, who has done a lot and longtime co-author of Romance, but not enough people know about it, and so I think that
Well, I usually say, well, there are two people who know something about it, and I'm not one of them. The other person is Athar.
well, know something.
Who knows more than I do.
No, yeah, I think between the two of us, we know a little bit now after writing this paper.
No, but I want to say that what's really fascinating here, that if you contrast this Athar, you just put this B there into, well, you have B2, right? And B2 is distributed. And then the techniques are different. So essentially, what they're based on Ramsey's theorem, and the fact that just infinite Ramsey theorem can be formalized in this systems of second order arithmetic, actually provable as a scheme. So if you have, so this is Gaifman who in the 60s came up with this procedure, which is a uniform procedure that works without any assumptions of cardinality of the model.
Yeah.
And now, okay, so these are all distributed lattices, whatever they are, finite or infinite. It's all kind of very well understood. Now we move away from distributed ones. So that's the simplest one, or maybe the
one of the two.
Then you need different techniques, and you no longer have uniform results. All those results of this technique applies to countable models only. And nothing, absolutely nothing we know about what's happening in formalizing this to get results of uncountable one. And this is just like a small tweak in the construction. They're already in some sort of uncharted territory. So the question is, that you need those. Maybe there are other techniques, or maybe there are some models that exist for some completely different reasons. But so it would be good to sort of that's why we're trying both to popularize these results. And that's not easy to popularize.
No, and so this has been my project for the last like year or so. It's been the last couple of years, because we wrote the paper a couple of years ago, to first like write a good survey of the problem, what we know and how the techniques are, because it's not really explained how to use these techniques, because it's all in his head. And then to kind of go around and talk to people who would not have thought about this problem. So that was part of my project, was to try and talk to people who I think might be, it could spark, if it sparks something in the back of your head, I'd love to have a conversation with you about. And I'm around local-ish, so I can come around, and I'm actually I don't want to say something. Okay, I'm actually on sabbatical next semester, so I have some time to think about it.
Any other questions?
I wanted just to ask you if you know about another result, like Pudlak-Tuma result,
Yeah.
about that basically saying that representation of finite lattice as a congruence lattice of algebra, finite algebra is equivalent to representation of that lattice as an interval in a lattice of subgroups. I mean, it's just, reformulating it in a kind of
Yeah,
in a different representation, but at some point that was a hope that bringing this is actually into realm of group theory would be correct way to go.
good. So that's great. I forgot about that. So this is in Roman's book. So this is in the book. So the book that in chapter 4 of this book that I have of the structural models of Peano Arithmetic, that I don't know much about that result, but certainly it was mentioned there, and so I don't know.
It's also representation of finite lattices to some extent. I don't never remember which result which requires the Pudlak-Tuma, but it's essentially one of the proofs.
I think it's
the results about diversity.
oh okay.
Because the further thing is sort of you look at those models in the structural lattice, and then the question is which of them are isomorphic to one another. In the distributive case, you can make them all isomorphic to one another if they have the same dimension, the same number of generators. But so here Jim used Pudlak-Tuma to prove some results about diversity. And diverse and non-diverse extensions.
Yeah,
so
this result was
Jim knows about Pudlak-Tuma there, but we don't know much.
we don't. So the answer is no, I don't. But yes, someone does know about this.
There is someone to that.
I do remember that reading about that in one of these papers. Yeah, I'm surprised that came up. That's really. I mean, that's good that came up. That means that there's something to think about there.
Okay, anything else? All right, let's thank the speaker again.